Hello, and welcome to this topic, the application of a definite integral, work. In physics, we learned that if an object moves a distance d along a line where subjected to a constant force F in the direction of the motion, then the work done by the force is equal to the force times the distance. That is, W is equal to F times d. If force is measured in newtons, that is, the force required to give a mass of 1 kilogram, acceleration of 1 meter per second, then the work is done in Newton meters, also called joules. If force is measured in pounds and distance in feet, then the work is in foot-pounds. For example, a person lifting a weight, force of 3 newtons, a distance of 2 meters, does 3 times 2 joules of work. Strictly speaking, a force slightly greater than 3 newtons is required for a short distance to get the package moving upward. And as a package near the height of 2 meters, a force slightly less than 3 newtons is required for a short distance to get it stopped. Even in this case, the work is 6 newtons, but this is harder to show. Similarly, a worker pushing a cart with a constant force of 150 pounds in order to overcome friction, a distance of 20 feet, does 150 times 20 is equal to 3,000 foot-pounds of work. In many practical situations, force is not constant, but rather varies as the object moves along the line. Suppose that the object is being moved along the x-axis from A to B, subject to a variable force of magnitude f of x at the point x, where f is a continuous function. Then, how much work is done? The strategy of slice, approximate, and integrate leads us to an answer. Here, slice means to partition the intersection AB into small pieces. Approximate means to suppose that on a typical piece from x to x plus delta x, the force is constant with value f of x. If the force is constant with value f of xi over the interval xi minus 1 to xi, then the work required to move the object from xi minus 1 to xi is fxi times xi minus xi minus 1. Integrate means to add up all the bits of work and then take the limit as the length of the piece approaches to 0. Thus, the work done in moving the object from A to B is W is equal to the limit of the Riemann sum of fxi times delta x. Now let's apply it to spring. This is a spring. According to Hooke's law in physics, the force f of x necessary to keep a spring stretched or compressed x units beyond its natural length is given by f of x is equal to kx. Here, the constant k, the spring constant, is positive and depends on the particular spring under consideration. The stiffer the spring is, the greater the value of k. Now let's see example 1. If the natural length of spring is 0.2 meter, and if it takes a force of 12 newtons to keep it extended 0.04 meter, could you find the work done in stretching the spring from its natural length to a length of 0.3 meter? We know here the force varies with x. It's not constant. So it's a function of x. We need to apply the integration to find the work. Let's find the spring constant k first. Then we can get the force function and find the work by integration. Now let's solve it. By Hooke's law, the force F required to keep the spring stretched x meters is given by f of x is equal to kx. To determine the spring constant k for this particular spring, we know that F 0.04 is 12. That means k times 0.04 is 12. Or we can solve that k is 300. So f of x is equal to 300 times x. When the spring is at its natural length of 0.2 meter, x is 0. When it is 0.3 meter long, x is 0.1. Therefore, the work done in stretching the spring is W is the definite integral from 0 to 0.1. It's an integration of the function 300x. And we can easily solve this definite integral and to find the work. All right, that's all for this section.